Today I'll be interviewing some experts about climate change. I made a video explaining how the Milankovitch cycles impact our climate. Many of you wrote in comments and critiques. I got over 12,000 comments on those videos. But I'm not an expert on this topic, so I've invited 3 guests to answer your most frequently asked questions. This is a contentious subject, so I wanted to get serious scientists, but I wanted to get different opinions, and my guests definitely have different opinions. This is a controversial subject. As you know, people on the internet are normally extremely polite. They would never even think about writing mean, nasty comments. But in the unlikely event that this does happen, I want you to be kind to these people. They probably need a hug. Before we get to the interviews, I have an apology to make to the nation of Serbia. I have been mispronouncing the name of one of Serbia's most beloved scientists. So to help me out with this, I've invited a special guest, Miljana from Serbia.
Ćao, dobro večer svima, drago mi je da ste tu. Ja sam Miljana i ja sam iz Srbije i ovdje sam da vam pomognem da izgovorite ime Milutina Milankovića na srpskom.
So how do you pronounce this man's name?
It is Milutin Milanković.
Thanks so much. Now I have 3 guests with very different opinions. People often just want to hear the opinion that they agree with. I think this is why we're so polarized. People all want to be in their own safe little bubble. So I think you should watch all the interviews. But if you just want to hear why you shouldn't worry about greenhouse gas emissions, you can skip to Judith Curry at the 36-minute mark. If you just want to hear why you should worry about greenhouse gas emissions, you can now listen to Simon Clark and then Ben Cook at the 117-minute mark. My first guest is Dr. Simon Clark. Simon studied atmospheric physics at Oxford. For his PhD, he studied the physics of the Earth's atmosphere. He has a great YouTube channel. He's written a book called Firmament about the history of the atmospheric science. We know that water vapor is the main greenhouse gas. Why are CO2 and methane levels important when most of the greenhouse gas is caused by water vapor?
It's a really great question because people do get so hung up on CO2 and methane they don't talk about water vapor. The basic answer is we're not directly forcing water vapor. Water vapor acts as an amplifier for other changes in the radiative forcing of the atmosphere. So if you put CO2 into the atmosphere, for example, if a volcano erupts and adds lots of CO2 to the atmosphere, that CO2 will warm the planet slightly, but the bigger effect is that by adding CO2 to the atmosphere and warming the planet, you allow more water vapor to be trapped in the atmosphere. And that water vapor acts as a powerful greenhouse gas. So it amplifies the impact of that CO2. And so what we see with anthropogenic warming is by adding CO2 to the atmosphere, sure, we're directly warming the planet, but most of the warming that we see is because of that water vapor feedback. So water vapor is super important. It's the most important greenhouse gas, but it also responds to changes in those other greenhouse gases. And that's why we focus on changes in methane and CO2 in particular.
Is there anything in my videos that you think is inaccurate or misleading or anything important I left out?
I mean, I don't think so. I mean, I think watching it, I think you hit all the major beats. The only thing that I personally would have put in is a little bit of the history, because there's an amazing story about a guy called James Kroll who did a lot of the science, but that Milankovitch basically then took and refined, which normally wouldn't be that interesting, but Kroll was a janitor at a Scottish university, and he came from this really humble background and ended up doing this world-leading climate science, and unfortunately was slightly wrong. And Milankovitch came in and corrected some of his mistakes and got all the credit.
If we look at the geological record, we often see that CO2 levels will increase after the temperature has increased. This suggests that temperature changes are causing changes in CO2 levels, not the other way around. What's going on here?
Yeah, so I think people get trapped in this false dichotomy of it has to be CO2 increases and that increases temperature, or temperature increases and that increases CO2, right? And the answer is both of those things happen. Like, there's complex feedbacks that take place. The radiative forcing, so like my background is as a physicist, I can definitively tell you that if you add CO2 to the atmosphere, you will radiatively warm the planet. That's like one-to-one correlation. But what also happens is by changing the temperature of the planet, you change the balance of the carbon cycle. And so you then can add more carbon into the atmosphere. And so what you see is when we come out of ice ages, there will be a certain amount of warming that will happen that will then cause CO2 changes. And then vice versa, you'll see a certain amount of CO2 change that will cause the warming. We know that about 90% of the warming takes place as a result of those CO2 changes. So both of those processes happen, but we are very confident that the majority of the warming takes place because of CO2 increases. And that's what we've seen on geological scales, right? This is something that you see looking through the geological past, and that's why we can be so confident, along with other reasons, why we, by adding CO2 to the atmosphere, are causing the warming that we observe. There are other factors beyond just the geological record.
Like, why would temperature increase cause CO2 levels to rise?
The two major feedbacks would be, by increasing temperature, you melt permafrost, right? So you have stuff that's buried in the ground in the very high latitudes, like methane, for example, that's trapped in the permafrost, that when the permafrost melts is released into the atmosphere. There's also a feedback where by increasing the temperature of water in the ocean, you increase the amount of carbon that gets released from the ocean. And those atmosphere-ocean carbon feedbacks were actually one of the things that really tipped us off to this being an issue in the 1950s with people like Roger Revelle. So there's like really important feedback that takes place there that it took us a while to get the hang of, but like we ruled out the fact that this was the temperature horse drawing the CO2 cart. I had to think about the metaphor there.
You mentioned like several terms like radiative forcing. Could you just define for people who don't?
So radiative forcing refers to the energy imbalance. So remember that there are different ways that you can transmit energy. You've got conduction, you've got convection, and you've got radiation, right? Radiative forcing is where there is an imbalance in how much radiation is entering the Earth system and how much is leaving the Earth system. So if more energy arrives than leaves, then you've got radiative imbalance and the Earth will warm up. Conversely, if suddenly more energy started leaving the Earth system than was entering, there'd also be a radiative imbalance, but it would result in the Earth cooling.
You said we were able to figure out, like, you know, that CO2 was driving the temperature change rather than can you just like how do we know that?
It's a very valid question, and I think this doesn't get talked about enough. So for me, the real smoking gun, the fingerprint of why a greenhouse gas is responsible, it might not be CO2, but we know that there are these large changes in CO2 and methane concentration, is that the atmosphere is warming more close to the surface, and it's actually cooling in the upper atmosphere. So if the atmosphere was being warmed because of an increase in the amount of energy coming in from the sun, for example, then you would expect the atmosphere to warm, maybe not uniformly, but there would be warming throughout the atmospheric column. Whereas if you increase the amount of a radiatively active compound like CO2, meaning that it absorbs long wavelengths of radiation, then that warming is intensified closer to the surface, and because it's absorbing long wavelength radiation, that means that long wavelength radiation doesn't reach the upper part of the atmosphere. And so the upper part of the atmosphere cools down. So if you were just to a priori say, what would I expect to see happen if I'd increase the amount of an insulating compound in the Earth's atmosphere, you'd expect to see warming close to the surface and cooling higher up. And that is exactly what we see. It's exactly the opposite of what you'd expect to happen if you saw an increase in radiation coming in from the sun, for example. So that vertical profile in warming is like the smoking gun for why CO2 is responsible. And the other thing that we don't talk about enough, I think, is that the chemical composition of CO2 in the atmosphere, carbon in the atmosphere, full stop, indicates that it is fossil fuel carbon that has been added to the atmosphere, and it's not volcanic carbon. So we know that there's different isotopes of carbon. You've got carbon 12, 13, and 14. And we know that carbon 14 is created by cosmic rays, and it decays with a certain half-life. So you've probably heard of carbon dating. The older an organic object is, the less carbon 14 there is in its different sort of mix, its flavor mix of carbon. And what we've observed over the past several decades is the relative proportion of carbon 14 in the atmosphere has decreased. And that tells us that there is an injection of carbon into the atmosphere that must be very, very old, so that there's basically no extra carbon 14 being added to it. And that, we can pretty neatly deduce, means that it's very old, fossilized even carbon that's been dug up, burned, and then added to the atmosphere. So those two extra factors, I think, are the smoking gun that it is carbon that's responsible, and it's deep old carbon that we've dug up that's responsible.
There's kind of what I think of as like a positive feedback loop where like temperature can raise CO2 and then CO2 can also raise temperature. There must also be some negative feedbacks where this would like, wouldn't this would run away.
Yeah, and this was one of the early criticisms of this theory of orbital changes forcing changes in climate, because people were like, surely Milankovitch, surely Mr. Kroll, you must be completely wrong, otherwise we'd all be cooking. And there are negative feedback. So the one that's sort of most contentious in that we still need to nail down the error bars on it is cloud cover. So the more you warm the planet, the more water vapor you add to the atmosphere, and that means that you have more clouds. So that means that when the clouds are sort of low, you'll reflect that they're white clouds, so they're reflecting more sunlight away. So the warmer the planet gets, the more clouds you add, the whiter the planet becomes, the less energy suddenly becomes available to the planet, and so it will cool down. So if that was the only feedback in town, then you would always J-curve back to some equilibrium temperature. But unfortunately, but kind of fortunately, because it makes life more interesting, you do have multiple different feedbacks, some positive, some negative.
So in my videos, I talk about the Milankovitch cycles and I talk about CO2 levels. How important are other things like solar activity and volcanoes for climate change?
Changes in solar activity, we know, have an impact on the climate over very long timescales, and we're talking more like hundreds of millions of years. Volcanic activity is massively important. I mean, we think the...
Wait, but are you talking about the Milankovitch cycles, or are you talking about changes in the solar output?
In that case, I was referring specifically to changes in solar output. I mean, we know that orbital forcing in Milankovitch cycles, we know that that's really important, and that's what we're pretty sure that that's what's forcing the ice age, the cycle of ice ages and interglacials. But also, there are changes in solar output over very long timescales, and we know that that has influenced the Earth's climate. But on geological timescales, we also know that volcanic eruptions, volcanic forcings of CO2 have been very important. We believe that the Permian mass extinction was caused because of extensive volcanic activity. We think that the Cretaceous mass extinction that killed off the dinosaurs was at least partly caused by an increase in volcanic activity. So looking through geological and biological history, we see pretty clear evidence that volcanic activity has forced the Earth's climate. The difference being, A, we haven't seen any kind of mass eruption. Let me put it like this: I think we would have noticed if it would have happened with our various monitoring stations. And B, the time scale that these geological changes happen over is much longer than what we have observed climate changing over the past couple of decades.
How do we know the sun hasn't gotten brighter over the last 100 years or something?
I mean, people have been looking at the sun for a really long time, despite what everyone's mum has told them. And we have records of sunspot activity, and that is a pretty decent proxy for radiative output of the sun. We've seen that there is this cycle that takes place, and we know that that does very slightly vary the wattage output of the sun, but we haven't seen anything that correlates with the observed changes in temperature. So yeah, absolutely, that is a factor, but you're talking about a forcing of, I think it's less than 1/10 of a watt per square meter. It's really tiny compared to the observed radiative forcing that we actually have. And so I guess the answer is we've looked. Scientists have looked at this stuff for a long time.
I'm very curious about what you said about solar activity changing over very long periods of time. I thought the only things changing the sun solar activity over long periods of time were the Milankovitch cycles, and there's this thing where the sun over billions of years is getting brighter.
This is the faint young sun paradox, right?
Yes, and I have a video explaining why the sun is gradually getting brighter. But are there other things that would be causing the solar activity to be changing?
I mean, that's the only one that I'm aware of that is relevant over the course of hundreds of millions or billions of years.
Right. How worried are you about climate change?
Is it the thing that could end all life immediately in the same way that nuclear war could? No, it's not. In that sense, an international nuclear war is probably the number one thing that anybody should be worried about. But I put climate just under that. I mean, it's the thing that keeps me up at night. It's the thing that, by various mechanisms, makes me worried about the future that my daughter's going to grow up in. Because it's not so much that she's going to notice oh, my day today is 2 degrees warmer than it was for my great-great-great-great-great-grandparents. Like, that doesn't really make any difference. What makes a difference is the cascading impacts of that on food production, on biodiversity, on the fact that we're losing species at something like thousands of times the rate that, you know, we probably should be losing species. The thing that in Europe specifically that keeps me up at night is the potential collapse of the Atlantic meridional overturning circulation. If that happens over the course of a couple of decades, then Europe will cool by 20 degrees, and that's basically a return to ice age conditions. And it's something that we have no power to fix or to stop when it begins. So I think of climate change as this issue that has a mean response that worries me and is not great, but is like survivable if we get our act together. But it has these relatively low probabilities that are still way too high of absolute catastrophe. And something like the AMOC collapsing is one of them.
Sorry, what does that mean? The AMOC is
Atlantic meridional overturning circulation. Like the relatively low but too high for comfort probability levels of these tipping points being reached, you know, frankly scare the shit out of me. Like, it's something that I am intensely worried about, and it's something that could affect me in my lifetime. Like, it's entirely possible that, for example, the Atlantic circulation we could find evidence that it suddenly started shutting down, and by the time that I'm an old man, that'd be a big problem. But it's something that I'm more worried about as, I guess, like a parent and as someone who thinks of themselves as some kind of custodian of the planet for future generations. Like, it's not my planet. I'm just looking after it until future generations turn up. And my worry is that we are making life for those future generations way, way harder and giving them a planet that is way poorer in terms of the species of animals and plants that they get to enjoy. So does it worry me? Yeah, absolutely. It worries me directly, selfishly, but it also worries me in terms of what we are doing for future humans.
Mm-hmm. I think that's quite interesting that we're worried about global warming, but you're talking about like it affecting the circulation to make it too cold in Europe, which is really fascinating.
The average temperature changing is not really that significant. Like, it's the impact of really, the better way to think about this is it's not that the average temperature is increasing, it's that the amount of energy in the Earth system is increasing. And that shifts precipitation patterns. It means that some areas are going to get droughts, some areas are going to get deluges of rainfall that they're not prepared for, some areas are going to see more extreme heat waves, some areas are going to get cooler, some areas are going to get warmer. It just throws the whole system that is so finely balanced. Like, the entire biosphere is so finely tuned to the way that the climate has been. And yeah, it's changed, sure, but it changes over long timescales in a way that life can adapt to. And the thing that is so scary about climate change, the reason we should be worrying about it, is you're taking this incredibly delicate machine of brass cogs and levers and gears, and you're just smashing it with a sledgehammer. And you don't know what the impacts of that are going to be. Like, sure, the casing of the machine is going to be a bit dented, but like, is that really a problem? What is a problem is the internal workings of that machine are going to be damaged. And that could have impacts that rise to the surface and what that machine does that we don't fully understand, but we're pretty confident they're going to be bad.
I keep trying to nail down, like, okay, what does this actually mean, like, in terms of, like, our future? And I feel like there's so much unpredictability. You're, like, saying, oh, there's all these risks, you know?
Yeah, with the mean response, we are becoming increasingly confident in, because our models are getting better and better. And we can say that they're getting better and better because we test them on the data that we've got up to date. Like, you run them backwards and say, right, can you recreate the past changes in climate that we know happened? And they're getting better at that. That's why we can be more and more confident that they're going to be accurately predicting what's going to happen in the future. So, like, the mean equilibrium climate sensitivity is one of these metrics, right? If you double CO2 in the atmosphere, what's the increase in temperature going to be? We're narrowing the error bar on that more and more. We're becoming increasingly confident. But those risks that I talked about, those tipping points in the Earth system, rely on internal dynamics that we can only approximate. Like the example of the Atlantic circulation, right? That's a complex interaction between oceanic dynamics and what's happening in the atmosphere and what's happening in Greenland in terms of ice melting, which is itself like horrifically complicated. And it's especially complex where it's not just physics at play or chemistry, it's humans. It's, well, this is the trajectory that we're on at the moment, but like What happens if everyone decides that we're just not going to bother with net zero? It was too much work. Like, what does that mean for 2100? So predictions become harder when you add in that human element to it.
I mean, what probably most people are curious, okay, what is going to happen if we do nothing?
Yeah, I mean, the business as usual. Well, the business as usual trajectory used to be really awful. It used to be like 4, 5 or more degrees of warming by 2100. And that's the situation where pretty much all the climate tipping points that we're aware of, the kind of things that I mentioned, would be hit. Like, you would be looking at the Atlantic shutting down. You would be looking at the Amazon dying back and permafrost melting and all this stuff. But the business as usual trajectory has been doing this interesting thing recently where it's so much cheaper now to do things in a low carbon way than on a level playing field. People would just be using renewables. They wouldn't be using oil for generating electricity, for example. Like, the business as usual trajectory of us just taking our hands off the wheel and trusting the market to do what it wants to do looks so much better than it used to because we took early action. And now we have these solutions. We have these technologies. So if we were to suddenly just take our hands off of the wheel, I mean, usual caveat of there's error bars on this, but you're looking at a couple of degrees of warming. I stick my neck out and say you're probably looking at maybe 2.5 to 3 degrees of warming, much less than we did before. But that's still a level of risk that is, to me, at least, unacceptable.
All right, we mentioned climate models. Like, how good are these models?
Yeah, I mean, and this is a completely fair question. And I think people who don't look at this for a living, right? Like, you just hear model and you think, well, they don't really know what they're doing. Like, this is approximating, right? The thing to remember is that all models are wrong. It's just that some models are useful. And a model is useful if it can recreate what you expect to happen. So I already mentioned, we can put in, look, this is the change in CO2 concentration in the atmosphere over this past century. This is the change in radiative forcing. If you're getting spicy, you could say, this is the change in forest cover. This is the change in how we've been using the land over the past century. And you can ask a model, what does the temperature series look like for the 20th century? And our models are getting better at recreating what we've actually observed. So they are getting better and better. They're not perfect because no model is perfect. Every model is wrong. But they're getting better and better at recreating what we've already seen, which means that we can be more confident, given that we understand the underlying mechanism of what is causing the change, of what's going to happen in the future. As for how well we can reconstruct the past, this is the field of paleoclimatology. There are lots of different ways that we can reconstruct the temperature record in the past. You can use tree rings, you can use beetles, you can use stuff that you find in stalactites and stalagmites in caves, you can use ice core analysis, any number of technologies. And that's actually a really important point, is that it's no one technique that you're using. It's no one ice drilling site, for example, because all that tells you is what happens at that specific site. That's what the local temperature changes look like, and it gives you some information about global temperature change. By combining lots of different sites, lots of different ice core sites, with lots of different cave record sites, with tree ring sites, with all these different techniques, that's when you get to reconstruct the global temperature. And the kind of most famous one of this was the Michael Mann hockey stick, which showed this long, relatively straight handle and then suddenly an uptick in temperatures. And we showed that actually that was not the whole picture. There was a paper which I wish I could remember the citation of. I'll send you the link to it if you like. That basically said, yeah, it was kind of right, but actually the hockey stick is straighter and it's longer. And the uptick is so much more pronounced than what Michael Mann and his co-authors thought. Our error bars are shrinking. They are still there. It's not science if you don't have an error bar. And obviously, the further you go back in time, the larger those error bars become. And, that applies right the way back to way further than the past couple of 100,000 years. Like, if you're talking about reconstructing the past hundreds of millions of years, you can look at geological data. You can use things like the geocarb model to reconstruct approximately what the temperature was like with a resolution of like millions of years. But in terms of like the past hundreds of thousands of years and the past million years or so, you can get relatively fine detail and you can get those error bars to be relatively small, and that we can have a pretty high degree of confidence in the findings of what the Earth's climate has looked like for the past million years or so.
I understand we have lots of ways of measuring what the temperature was, but like, how well do we know what caused all these different temperature changes? And you look over the past million years, you see all these fluctuations, and like I look at it, like I can't make any I can't see any patterns in it. I'm like, do we know why the Earth did that?
Yeah, I mean, I think it's fair to say that you look at a time series like that and you're never going to know exactly what caused every individual wiggle. The best that you can do is to tease apart the long arcs of what's going on. Because, for example, like a volcanic eruption, like a large eruption like Pinatubo in 1991, for example, that cooled the planet by the best part of a Kelvin over the course of 18 months. And that could be a massive blip on a geological time series, right? Like there could be a volcanic eruptions that we just don't know about. Well, that would be why the temperature dipped in a certain year, or it could be that there was some other local factor, like I don't know, massive wildfires or something that led to lots of soot being put into the atmosphere, and that reflected light away. So there's noise on top of our reconstructions, but the key thing is that you can reconstruct those longer arcs of this stuff we can we can be pretty statistically confident that that's attributable. We can do a regression and assign it to a Milankovitch cycle, or we can assign it to changes in solar radiation, or we can assign it to changes in CO2. It's absolutely correct to say that you can't perfectly account for every wiggle on the graph, but you can, and especially this is more the case the closer and closer you get to the present, you can reconstruct the larger scale time series. And over the past, say, 200 years, you can pretty definitively say, this is the physical mechanism that caused this, because we know there is this direct link between CO2 levels and the average planetary temperature, or between this type of volcanic eruption and planetary temperature.
Can we say with confidence, like, this is what caused the medieval warm period, and this is what caused the little ice age? Do we have that level of like confidence?
Yeah, these are the thing to mention about the medieval warm period, the Roman warm period, the Little Ice Age. These are all we're pretty confident regional effects, right? So it may be that one particular region in the medieval warm period, like Europe specifically, was warmer than the background, but if you look elsewhere, then you don't see such a strong signal. There are various hypotheses for like why that would be the case. This is not an area that I'm a particular expert in. There are various things that you could talk about, like the North Atlantic Oscillation, so changes in average pressure over the Atlantic. You could talk about El Nino. There are various internal dynamics that people point to. I'm aware that there are studies that have been done that have attributed those specific warming periods to those dynamics. I personally don't know the details of those, and I'm not sure what our confidence level is in assigning them to specific internal dynamics. I'm afraid you'd have to ask somebody better qualified about those specific things.
So a lot of my second video, I talk about this paper that argues that like agriculture had all these important effects on climate, and that the climate would have gone into more like a glaciation event, but this stopped it. And I get a lot of criticisms about this, and I also I'm a little unsure about this, because it seems like the amount of CO2 we were talking about is not a huge amount. Is that really that? Because that would imply, okay, it was only I think 20 parts per million CO2 level or something. That would imply our current levels of CO2 would be utterly catastrophic, almost right now. I worry I may have exaggerated the effects of agriculture. I'm trying to figure out all what's going on there.
I have to admit, when I was watching the second video, I was thinking that this was just going to be this was going to be the lead-in to modern emissions, and saying, well, we know that it warmed this much, and this is how much we're adding to the atmosphere now, so this would imply this much warming. The honest answer is I don't know actually what the impact of early agriculture was on climate. That's not a paper that I'd heard of before. It's not a paper that I've read. I'd have to go through and read the specifics. Obviously, the CO2 effect is logarithmic. To begin with, a step change in CO2 will produce more warming than the equivalent step change will at a higher concentration. But I don't know. I would be surprised if it was as important as you implied in the video. But I'm hesitant to say anything beyond that.
Well, so many people were saying, we know why climate is warming. It's because, we're getting out of a Milankovitch cycle or something. And
which you very clearly demonstrated was not the case. Like, you can very clearly point to, well, okay, sure, this forces the climate, but, like, this is where we started on the graph and this is where we are on the graph.
Right now, where we are in the cycle, we should be at a cool period. But I also think, and I may have gotten this a little wrong in the video, because the cycle doesn't exactly translate to what the temperature should be, right? And I think thinking of it that way, we should be at a really cool period. It should be like we should be covered in ice right now, based on where we are in the cycle. But that's not really true, because the planet warms and then all this ice melts, and that has lasting effects.
Yeah, absolutely. Yeah, it's not an instantaneous thing. Like, there's the lag in the system of gradually you lose ice cover because it's glaciation. There's loads of weird, funky internal dynamics that happen. So that's like there's a delay in the temperature impact of it, and then there are other factors on top of it besides just the Milankovitch cycle. So it's I think you did the right thing to point out that, like, well, okay, zoom out. Like, this is where the whole cycle is. Zoom in. This is what the expected change is over, like, this specific time period. And this wouldn't... Okay, from one angle, this wouldn't explain what we've currently observed. But from the other angle, you're like, well, here's... And it's sort of Occam's razor. It's like, well, here's another factor that we know forces global climate. And we know that the underlying factor behind that has changed over the same time period. So, like, just the Milankovitch cycle on its own isn't proof that it's, this is what should be happening, right? Because it's not the only cycle in town, you have to account for all the other information.
One thing I hear is, like, CO2 levels are saturated. What's going on there?
Yeah, so the effect of CO2 on the atmosphere is logarithmic, right? Like, if you double CO2 in the atmosphere, you produce a certain amount of warming. But if you double it again, then you don't produce the same increase in warming. There's a curve that drops off, right? Because if CO2 was a linear warming force, then, like, Venus, for example, would be trillions of degrees, and it's only a couple of hundred Kelvin warmer than Earth. So there is this point at which, by adding more CO2 to the atmosphere, you're not increasing the temperature. But we know that it's not saturated because we have satellite measurements of it. There are 2 satellites where you can compare the time series of the long wavelength radiation that's reaching out into space. And if you basically subtract one of those from the other, then you can see that there are these dips. There are very specific dips in the wavelengths that are escaping to space. And because we can predict using molecular theory how different molecules absorb different wavelengths of light, we can say, right, that dip is because of increases in CO2, that dip is because of increases in ozone, that one's because of methane, and so on. So we know that it's not saturated because there have been observed changes in the relevant sections of the electromagnetic spectrum over the past couple of decades. There is some confusion about this because in one part of the spectrum that gets absorbed by CO2, yes, it is saturated, but it's the other parts of that spectrum, and specifically it's the edges of the wavelengths that get absorbed, because it's not like a step change, like there's a smooth curve of which wavelengths get absorbed. It's the edges of that bit that is saturated, where by adding more CO2, you are increasing absorption in those wavelengths. So I can flippantly say, no, it's not saturated. And I can say that because we have experimental evidence, and then we have the theory to back up that actually we know what to look for, and hey, bingo, that's what we get from the satellites.
I'm just curious about some other thing. I'm actually, like, debating if I want to make another... I'm going to get so much hate on this.
Oh, welcome to my world.
I'm like, do I want to put this out and get, like, so much crap from everybody? I'm sure what I deal with is not what you deal with.
Like, I have very explicitly made videos that are targeting people who are skeptical of climate change, and I know that they reach the right audience because the comments are dreadful.
I know what I'm going to get is, like, if I interview you, you're like, oh, why didn't you talk to this other guy? And they'll mention their favorite crank scientist.
Judith Curry or whoever, yeah.
I don't think they're all cranks. Like, I feel like there are some legitimate concerns, and I'll also, like, I just, well, mostly I'm just I don't know who to trust here, and it's just like it's very confusing for me.
The thing that people miss about the climate skeptic movement is that like skepticism is a fundamental part of science. Like it's not science unless you have people who are saying, "Hang on, I call bullshit on this." Like, where's your proof? You know, that's a really valuable thing to have.
Yeah, I mean, I do actually kind of, I really want to find someone that's like a little bit on the, not crazy, but a little bit on the skeptical side to interview. Because
Yeah, yeah, that's the thing. There are several scientists who, like, I think started out entirely reasonably being skeptical of this new thing that was coming out. And it was like, cool, I want to see definitive proof of this. And I think there are just some people that, like, no matter what evidence you present with them, they're just never going to change their mind. And so there are Judith Curry is another one, Stephen Koonin is another one that people know, Bjorn Lomborg. There are these people who are just like, yeah, I've heard you, but I don't believe what you're saying. Like, I'm very much of the like opinion of trust the scientific consensus, but I do see the merits of having these like people who come from the outside and challenge it. Basically, I don't think these people are right. Based on what I've done, based on the literature that I've read, and when I've done analysis, I guess I just disagree with their conclusions.
Thank you so much, Simon Clark. So Simon told me I should not interview Judith Curry. I hope he's not upset when he learns that my next guest is Judith Curry. Dr. Judith Curry got her PhD at University of Chicago, where she studied the weather and climate dynamics of the Arctic. She has held faculty positions at Purdue, Penn State, Colorado Boulder, and most recently Georgia Tech, where she served as chair of the School of Earth and Atmospheric Sciences for 13 years. She is currently president of Climate Application Network. She's written a book called Climate Uncertainty and Risk. How fast is climate changing compared with other periods in Earth's history?
Well, climate has always changed for, the 4.6 billion years or so that the planet has existed. What we know about past climate change comes from paleoclimate analyses, sediments, ice cores, this kind of thing. But the point is, these proxies, these paleoclimate proxies, have coarse temporal resolution. I mean, say even for like the past 1,000, 2,000 years, the resolution is maybe 50 years. And if you go back for the past 8,000 years, maybe the resolution is 300 years. So relative, to this coarse resolution, the modern warming that might be attributed to fossil fuels is really only about 40 years old, since 1980. That's when we saw, an uptick in warming started. So this is within the noise. If there have been periods in the past that have warmed at this same rate, we wouldn't know about it because the information we have isn't able to resolve, this kind of time scale.
Okay, so I mean, I'm sure you've seen the graphs where they have, a long period of like very stable climate and then a spike at the end. But you're saying that we just don't have the resolution in that graph.
Okay, first off, the hockey stick graph,
Yeah,
is fictitious. I mean, it's got a lot of bad data in it and a lot of bad data analyses. You look at more realistic reconstructions, and you do see the medieval warm period and the little ice age, but these were events of several hundred years in terms of trying to pick out a period of 40 years that has a warming that we've seen comparable to the past 40 years. We just don't have the resolution in the data to do it.
can you explain a little what are some of the problems with the hockey stick graph?
Oh, I mean, they're endless. I mean, we could spend, people have written books about this. I mean, basically, there was a lot of data that it relied on tree ring data. First off, tree ring, it's very difficult to deconvolve a temperature signal from the precipitation signal and the CO2 signal. So it's very difficult to sort these things out. Michael Mann's hockey stick exercise cherry-picked and mislabeled a lot of data. So there are big data quality issues, and the statistical methods that he used to analyze the data were not robust for that kind of a project, and were pretty much designed to give you a hockey stick. And basically it came down to just cherry picking a few time series to get the desired signal. So it was a very, very shoddy piece of science, in my opinion.
I don't think I've seen other graphs from other people. I don't think he's the only one.
Oh, but they use the same data. They use the
Okay.
same methods. Okay.
Well, you
I mean,
mentioned tree rings. Is ice core data any better, or?
well, it has problems too. First off, I mean, you only have ice cores, long ice cores in a few locations like Greenland and Antarctica. And those ice cores are not, those locations are not necessarily representative of global climate, but there's a lot of uncertainties in timing and interpretation, even of the ice core records. So, I mean, I think the ice core analyses are certainly much better than the tree ring analyses. But when you get down to representativeness, how those regions would represent the global climate, well, not really.
But we do know the planet has been warming over the last 40 years.
Well, overall, it's warmed
Or-
since the mid-19th century.
Yeah.
We had a period of warming in the late 19th century through the early 20th century. Then we had a period of cooling between about 1945 and the late 1970s. And then warming kicked in again around 1980.
Okay. And do we know how much of this warming is caused by human activity?
No. And then until we sort out the natural causes of climate variability on those kind of time scales, we can't really sort out the human cause. I mean, the sensitivity of the global climate temperature, the global average surface temperature, to increases in CO2 is uncertain by a factor of 3. Now, this isn't a number I made up. This is a number that's cited in the IPCC assessment reports. The uncertainty could even be larger. So, we don't have a perfect understanding of how much warming we should have received from carbon dioxide. And we don't have an adequate understanding of some of the natural contributions to the warming. So, I mean, we don't know. I mean, but by focusing on a narrow thing, the CO2 driven warming, I mean, we've really completely neglected natural sources of warming and climate variability. The same thing with the hockey stick. That whole paleoclimate community has spent the last 2 decades trying to defend Michael Mann's hockey stick rather than trying to develop new methods, collecting broader samples and working with real statisticians to analyze the data. What we end up with is an ever increasingly confident consensus to support a particular political agenda.
Okay, so what are the possible sources of natural variation?
Well, the sun is a big one. It impacts things on all time scales. And it's not just the heat coming from the sun, it's also the indirect solar effects, the spectral distribution of the radiation, magnetic field, cosmic rays, all sorts of things like that. The sun influences the climate in indirect ways. So these so-called indirect solar effects, we don't know enough about them, but there's a potential for these to have a much larger influence than people think. Early on in this, people say, well, what about natural variability? Well, the rate of global warming is going to be so great, it's going to swamp out anything from natural variability. Well, the only way to get that huge rate of global warming from CO2 emissions is to use implausible to impossible emission scenarios, the so-called 8.5 scenarios. So for all these alarming predictions, I mean, and you get 4 to 5 degrees centigrade of warming, in 100 years. Well, I would say, yeah, if you're going to get that much warming from CO2, yeah, I agree, you can ignore natural variability. But now we're down to a much more realistic projections or expectations of warming, maybe another 1 to 1.5 degrees centigrade for the rest of the century. When you're talking about those levels of warming, okay, then natural variability becomes of at least equal importance. In addition to the sun, you have volcanic eruptions. Since 1850, it's been a very quiet period in terms of volcanoes, but in the early 19th century, there were 3 mega volcanic eruptions, including Tambora, the year without a summer, which completely, changed the climate for some decades. Even the latest IPCC report said that if something like that was to happen in the 21st century, that would completely change the trajectory of 21st century climate change. The biggest factor on multi-decadal timescales, in my opinion, is the ocean circulation patterns. Again, the ocean has internal variability on timescales from a few years, like El Nino, to millennial timescales. And of greatest relevance to the timescales that we're looking at, say, 50 to 100 years, is the Atlantic multi-decadal oscillation and the Pacific decadal oscillation. And these have, they're not cycles, but they do have shifts. Okay, we're currently in the warm phase of the Atlantic multi-decadal oscillation and the cool phase of the Pacific decadal oscillation. I would expect, based on the historical record and paleoclimate record, that sometime in the next decade or so that we would shift to the cold phase of the Atlantic multi-decadal oscillation, which would have a big impact on our climate and the temperature trajectory. So these modes of natural variability are very important to the climate. And basically, they've been all but completely ignored in the rush to develop a consensus around fossil fueled warming.
Let's take some of these. So the volcanoes, wouldn't we have noticed if there were volcanoes causing the most recent warming?
No, they're not. No, it's the lack of volcanoes that are causing recent warming. But Hunga Tonga is an exception. Hunga Tonga was a shallow underwater volcano which erupted a couple of years ago and injected a huge amount of water vapor into the stratosphere, which has now wound its way around the globe. And in my opinion, is largely responsible for the spike, the warming spike that we saw in 2023, and that is still ongoing.
And also with solar activity, like, wouldn't we be able to measure changes in solar activity?
There are indirect effects on climate. Yeah, we measure the changes. We measure the magnetic field. We measure the insulation. We measure a lot of these things. But the issue is there are indirect effects of all this on the climate. That's where the challenge comes in, to actually unraveling those indirect effects on the climate.
What I'm hearing from a lot of people who are worried about this, they talk about these like different tipping points. What do we know about these tipping point scenarios?
Well, next to nothing. Nobody predicts a shutdown of the Atlantic overturning circulation on the timescale of the 21st century. People are disagreeing based on how they interpret the observations, whether it's speeding up or slowing down. Once we shift to the cold phase of the Atlantic multi-decadal oscillation, we'll see a new circulation regime in the Atlantic. There's a lot of natural variability going on. I mean, the idea is that melting from Greenland should make the waters more fresh. But the Greenland tends to melt when we're in the warm phase of the Atlantic multi-decadal oscillation. In fact, the recent bout of melting from Greenland started right around 1995 which is when we shifted to the warm phase of the Atlantic multidecadal oscillation. Once we shift to the cold phase, the melting from Greenland will slow down, for example. So there's a lot of factors in play. In fact, the Greenland melting has slowed down since 2012, really for a decade.
The argument that some people make is that like the Earth is just like finely balanced machine, that these organisms have been evolving over, millions of years for a particular climate. And if we mess with it, all these bad things will happen. Like, how is that the right way to think about this? Are these ecosystems fragile?
Earth's climate has never been in equilibrium. It has never been in equilibrium. No matter what kind of a time scale, it's out of equilibrium on the annual cycle. El Nino and La Nina pushes it out of any kind of an equilibrium, on time scales of less than a decade. So we are never in equilibrium. Okay, we always have natural weather variability from internal circulation, solar variations, volcanic eruptions. And yes, are there insults to ecosystems from weather and climate variability? Well, there always have been, and there always will be. Humans are insulting ecosystems more through our land use than through anything going on with the very slow creep of global warming. I mean, we're talking about, since pre-industrial period, about 2.5 degrees Fahrenheit. This is how much we've warmed. I mean, this is a very slow creep and it's a very small magnitude. And this is not, things like a volcanic eruption and a big El Nino really have more impacts.
I do want to get to some of the maybe more basic questions. A lot of people point out like that water vapor is the main greenhouse gas, so we shouldn't be worried about CO2 and methane.
Water vapor is the most abundant greenhouse gas. Okay, far more abundant than the other trace gases. However, molecule per molecule, the other trace gases pack a bigger punch, not CO2. CO2 packs a relatively small punch, but like methane and chlorofluorocarbons and things like that, they pack a bigger punch per molecule because of their molecular structure. And all of these have absorption and emission bands in regions of the spectrum that water vapor doesn't cover, so they matter.
So yeah, and water vapor is part of like a feedback cycle.
So is carbon dioxide, for that matter.
Right.
There's a whole feedback cycle involving carbon dioxide. So they're both feedback cycles.
Again, my videos were about the Milankovitch cycles, and that cycle itself wouldn't be that powerful, except it has like water vapor like amplifies this action.
Well, carbon dioxide, that anytime you change the temperature or the surface, like putting ice over the surface, you're going to change both the water budget and the carbon budget. These things happen all the time. There's feedbacks with any kind of change. You have a volcanic eruption that will stimulate some sort of a feedback, positive or negative, from both the carbon budget and the water vapor. So, the Earth's climate system is very complex. Mm-hmm. And once you bring in the solid Earth and ocean geochemistry and all that, into the Earth system, it's an amazingly complex system.
Well, you've kind of answered this, but people are like, that CO2 can't be causing global warming because when we look at the temperature record, we see temperature changing before CO2.
Like water vapor, CO2 is a feedback. Land surface processes, oceans are, if you warm the ocean, it will outgas CO2.
Yeah.
That's not to say that but if you have a volcanic eruption or a forest fire, that will add CO2. There's all sorts of, and if you have a lot of CO2 in the atmosphere, the vegetation will be happy and they will take up CO2, both on the land and in the ocean. So CO2 is a feedback every bit as much as water vapor is.
A lot of my questions are coming from people on the internet who are, I think, just confused. I don't think scientists are confused on this. A lot of people think it's got to be temperatures causing CO2 or CO2 causing temperature.
Tell them to go read a textbook on complexity, to just try to understand complexity, because we're dealing with a very complex system, and looking for simple cause and effect doesn't work in an exceedingly complex system. People are trying to convince themselves of a simple story and a fairy tale. And then they think, oh, the scientists are wrong or whatever. Our understanding, I mean, is very immature on this whole subject. You know, the data is inadequate. I mean, even now that, you know, people argue about the data and what it means and how to calibrate it and how to homogenize it and how to do whatever. But going back further in time, it's increasingly sparse. They think the scientists are trying to fool them. Well, maybe some are who are political advocates. The issue of concern to me is that there's a lot of people out there calling themselves a climate scientist. Maybe legitimately in the sense where they could study the economics of climate change or climate change in ecosystems. But at the end of the day, the climate dynamics, how the whole climate system works, this is a very narrow specialty. And, you know, people of my generation were trained in this area. There were no climate studies or climate impact studies or whatever that most of the people get their degrees in now, but hardcore atmospheric science, oceanography, and geology, geophysical sciences were what, you know, people of my generation were trained in. But the vast majority of people who call them climate scientists have these soft core degrees, climate studies or environmental studies, and they know how to recite IPCC talking points, but they don't understand in a fundamental way how the climate system works, and they can't critically evaluate, for example, what the IPCC puts out.
But the IPCC was created by climate scientists.
No, it wasn't.
No, it wasn't?
No, it was not. No, the political horse has been the policy horse has been way out in front of the science cart from the very beginning. I mean, there was an agenda. I don't know if you want to go through all this, but this was not created by scientists. They were given a very specific charge to focus on dangerous human-caused climate change with the explicit mandate not to look for any benefits of CO2 or warming, and to ignore natural climate variability. That was their mandate. When they tried to honestly meet that mandate in the first assessment report and the second assessment report, the UN Framework Convention was ready to shut them down. And in the summary for policymakers, the meeting with the policymakers and the second assessment report, they pretty much insisted that their scientists come up with an impact. So they came up with, there is now a discernible evidence of human-caused warming. And that was put in by the policymakers, and then the scientists went back into the second assessment report to change it to be consistent with that. I mean, this has been politically driven from the very beginning.
I don't know. I hear lots of different things. I mean, a lot of people say, you know, these skeptics are on the fringe of science, but I know you're going to disagree with that. But I still think, you're in the minority. I think.
Oh, not true. Okay, if you talk about people who speak out publicly, I'm in the minority, because scientists don't want to commit career suicide and have people like Michael Mann ruin their academic career like he ruined mine. Okay, anybody who speaks out, and you know, with the minority, people have deep understanding. They either keep their mouth shut, or they leave academia and go to the private sector or work for think tanks. I mean, it's so politicized. It is so politicized. It's terrible. Trusting what activist scientists say, anybody that you hear in the media, I don't think I'd trust very much unless you really listen hard to them and follow them over a long period of time. And if they're attacking other scientists, it's about politics. If they're overconfident, it's about politics. If they blame everything on climate change, it's about politics. If they go beyond in a more alarming way than what the IPC says, which is already political. That's politics.
No, well, let's get into the politics a little bit. Like, how did science get so politicized? I feel like most fields of science are this. I feel like this is an unusual situation.
It is, but it's environmental science isn't the only field like this. You've got public health, you've got a lot of biological fields, from GMOs to gender studies, a whole host of issues that have become acutely politicized. And anybody speaking out against what has become politically correct in academia gets ostracized, or papers don't get published or even sent out for review. They lose funding, they lose their academic positions. There's a horrible cancel culture in universities and in academia. And when I complain about in science, when people say, oh no, it's just as bad in social psychology and law schools and business schools, it's terrible everywhere. People in power in the academic professional societies, administrators, whatever, and they all tend to be of a particular political persuasion or have a particular dominant paradigm they want to push, they can enforce this. We're not going to turn it around, and we're not going to stop the warming, but we're talking about a slow creep of warming. Once you take out the extreme weather events, which haven't gotten worse during this period of warming, we're talking about the slow creep of sea level rise and the slow melting of glaciers. I mean, these are the real impacts of warming. Okay, and these are happening at slow enough timescales where we can adapt to them. And then the other thing that we've gotten bent out of joint is, why do we think that warming is dangerous? I mean, that there's nothing intrinsically dangerous. I mean, ecosystems overall prefer warmth, okay, to cold. People don't like warm winters. In the US, we've got people moving from Illinois and New York to southern states.
I mean, the sea level rise does seem like it can be a problem, because there are all these
sea level is rising 3 millimeters per year. If you stack 2 pennies on top of each other, it's this much. Okay.
Yeah.
This per year. I mean, you add it up,
it adds up though. But yeah.
Yeah, 8 inches over a century. Any place where sea level rise is a serious problem. Mid-Atlantic coast, New Orleans, Galveston, it's because the land is sinking. Okay. Maybe at the same magnitude or even greater than the sea level rise, particularly in the case of New Orleans. This happens because of groundwater withdrawal or the withdrawal of oil and gas. I mean, it compresses the ground. You build cities on this ground, billions of tons of cement. Of course, the land is going to compress and sink. So a lot of the so-called local sea level rise problems are really problems of the land sinking, or the way we've engineered the coast. A lot of New Orleans sea level rise problem has to do with engineering of the Mississippi River to avoid flooding. As a result, it's not carrying so much silt to replenish the delta. Okay, without that replenishment, New Orleans is sinking. So there's a lot of factors in play with regards to sea level rise. And the slow creep, like a foot a century kind of thing, is something that we can easily adapt to. There's evidence, paleoclimate evidence, that sea level in some regions was several meters higher than it is now, about 6,000 to 8,000 years ago. What we're seeing right now is not outside the realm. Anyway, the last ice age, sea level was 150 feet lower than it is now. So thinking, well, we need to stop burning fossil fuels to prevent, 3 millimeters per year of sea level rise. I mean, that's rather a joke. I'm no fan of fossil fuels, but thinking that you're going to stop sea level rise by stopping burning fossil fuels, that's a fairy tale.
What I heard is that, like, how do we know it's not solar activity? How do we know it's CO2? I was told that there was like the warming was happening near the surface. That if we could look at the profile of where the warming was taking place, and we saw that the warming was not happening in the upper atmosphere, was happening near the surface. I
That's a
think
myth.
that's
That's
a
a
myth.
myth. Both would give you the same profile in the upper troposphere, lower stratosphere, and the surface. I mean, that's a myth.
And then another thing I heard is that we can tell that the CO2 is coming from fossil fuels because of the change in the isotopes of carbon. Carbon that's been in the ground for a while will have lower rates of carbon-14.
And that's an oversimplification.
Okay.
In terms of how the carbon cycles through. I mean, the carbon, humans emit a fairly minuscule amount of carbon dioxide relative to what's in the atmosphere and stored in the Earth system and biota. I mean, it's a relatively minuscule. Yeah, you can see that signal, but the extent to what's causing the increased CO2, yeah, the emissions are contributing to it. But the fact that we're warming the oceans, we also have, ocean outgassing of CO2. We're changing the dynamics of the land uptake, and the sinks are all changing. So there's a complex carbon cycle and feedbacks that we understand qualitatively, but we don't have a quantitative understanding to be able to parse with 100% confidence that every single excess molecule of CO2.
Well, we're not saying that, but
but it's not simple. It's not that simple.
I thought we had pretty good records of CO2 levels going back quite a ways, and this is the highest it's been in quite a while.
It is, but the records that we have are ice cores, and people debate about how good that is. People who study the stomata in fossil records think that there was much higher variability. I would say overall this is the highest that it's been in a considerable while. But I mean, you go back way back, I mean, and CO2 was an order of magnitude higher at some times in geological history. So yeah, I would say, humans are poking the carbon budget, poking the carbon dioxide in the atmosphere, no question, in terms of our understanding of the CO2 sinks and all the feedbacks and how this is cycled and how this is disposed of in the ocean. Like I said, we don't, in my opinion, have a very good quantitative understanding of that.
I made this video about the Milankovitch cycle, and then all these people on the internet said, wow, you disproved climate change. And I really didn't think I had done that. The thing I couldn't figure out was that we should be in a cool period of the Milankovitch cycle. I couldn't figure out why temperatures were not dropping, over the last several thousand years. And
they have dropped since the Holocene optimum, about 6,000 to 8,000 years. They have dropped since then.
They have dropped. This paper was saying that that farming was actually responsible for increases, because there was, well, it wasn't just exactly farming. It was like the deforestation had like put lots of carbon into the atmosphere, and also rice farming had increased a lot of methane. And they looked at the past like 7 interglacial periods and saw that this one, like, you see an uptick. We normally see it go down, but in this case we see it go up. That was the argument.
The population was back then.
Yeah, but the argument was that that the population, a small amount of farmers actually could do quite a bit of there was quite a bit of deforestation, I believe.
On what fraction of land? Land is what, 30%, and that includes like Antarctica and Greenland. So if you get habitable land, I mean, we're talking about what, less than 10% of the Earth's surface, that even, deforesting all that, which I don't imagine that the small population back then did, is going to have going to change global climate in a huge way. It seems pretty implausible to me.
Why aren't we returning to like glacial conditions? Because we are at a cool period of the Milankovitch cycle.
We're in a cooling period.
Okay.
Interglacials have varying lengths. Let's hope that this is a long one, because people are worried about climate change, and they think a little bit of warming is bad. Well, do you really want, a mile of ice sheets over most of North America and Europe? So to me, that's a much worse thing that would happen. Yeah, I mean, are humans keeping the climate warmer than it would otherwise be? Probably.
You mentioned there were these solar indirect effects. Can you just explain a little more those effects?
It's in my, on a podcast like this.
Okay.
It's
It's too
awkward.
difficult.
Chapter 8 in my book goes into the natural modes of natural climate variability, including a fair amount of discussion on solar indirect effects.
And again, I've heard from other people that they were narrowing down the like climate sensitivity numbers, but I guess I'm getting not.
Okay. For decades, since 1979, the range has been 1.5 to 4.5 degrees. Okay. In the IPCC 6 assessment report, they narrowed it to 2.5 to 4 degrees. I think the narrowing on the top end was justified. The narrowing on the bottom end was not. There's been a follow-on paper. That IPCC assessment relied heavily on a multi-authored paper by Sherwood et al., who frankly didn't use a lot of the latest research on, paleoclimate data, and made some mistakes, various mistakes along the line. And there was a redo of that study by Nick Lewis. It was published in Climate Dynamics. And what he came up with was an average equilibrium climate sensitivity of 2.15 with a range of, I think, 1.8 to 2.9. Okay, which one of them is right? Well, Nick Lewis had better methodology, but it also shows how sensitive it is to assumptions that you make about various things in the paleoclimate record, about aerosols and things like that. So these assessments are uncertain, and I think that the 6 assessment report was unjustified to narrow it.
I don't know. I wish we could just lower the like vitriol and like hate on this topic, because like I think I may have made some mistakes in my videos, and it's just like, oh my gosh, like the I mean the people. Yeah,
I agree. Like I'm all about nonpartisan, and let's have a discussion. I have a blog, climate etc, judithcurry.com.
yeah.
There's a article up right now about the carbon budget. There was a previous article about solar recent, the latest two. But the point is, these are people who publish papers or publish books on the topic. They write an article, and people from both sides across the spectrum of the debate, a few actual climate scientists, other technically educated people who follow this very closely, they duke it out in the comment sections, and the author participates. I mean, very few of these issues are settled. The spectroscopy of the water vapor and CO2 and methane molecules, that's pretty much settled. But beyond that, there's a whole heck of a lot. In fact, almost all of it is unsettled. And as scientists, we should rejoice in that fact and try to push the frontiers of knowledge.
A lot of what I'm hearing from you is, like there's just a lot we don't know, basically.
You got it. This is an incredibly, I mean, you got your
I mean, is it still plausible that the like alarmist, I mean, like have we totally ruled out the alarmist scenario, or we just don't know?
Okay, yeah. Even the UN Framework on Climate Convention has now dropped the so-called 7.0 and 8.5.
No, I'm not saying that. Actually, no, I'm not saying that.
But
I'm
that's
saying
huge. That's cut the amount of
Okay.
predicted warming in half. Okay, down to maybe another 2 degrees Fahrenheit for the rest of the 21st century. This is what the UN climate negotiators are now working off of. How do you square that with all the alarm and the apocalypse and highway to climate hell rhetoric that you hear?
But we haven't ruled out that that there has been increase in global warming that's caused by humans. Like not 8 degrees, but we're talking,
Okay. We've seen 1.2 degrees of warming since the mid 19th century. Of that, an unknown portion greater than 0 is caused by humans. Is it 100%? I don't think so. Is it greater than 50%? Maybe. But we don't know because we don't adequately understand solar indirect effects or the contributions from the multi-decadal ocean circulations. So we don't know.
Just don't know. Okay. That's not the most satisfying answer, but
no, it's not satisfying. This is not a simple problem. Not a simple problem. And we shouldn't expect it to be a simple problem.
Well, this was a very engaging discussion. I think we got through my questions. I'm like a little nervous to put anything on the internet about this because I know how much hate I'm gonna get it from both sides. So yeah.
Well, let's see.
I'm sure you get way more than me. I'm sure you get.
Yeah. I mean, but I reckon if you're serious about this subject, go read my book. People from both sides come after me because I don't, uncertainty is a dirty word, okay, in the alarmist community. And I'm not sufficiently negative for what I would call the denier community.
Oh, really?
Okay. So, I mean, I sit in the middle on this with what I believe is an honest assessment of what the uncertainties are in all this.
Okay.
Start by reading my book, Climate Uncertainty.
All right. Well, thank you so much for doing this.
All right. Thanks. Been fun.
All right. Judith Curry was very critical of the famous hockey stick graph. I wanted to understand where these criticisms were coming from. I looked at a bunch of different articles and videos, and most of these were very technical and didn't make a lot of sense to me as an outsider. But I did find a video by Ross McKetrick. He's an economics professor. I don't know if he's right, but he was able to clearly articulate the criticisms. I'll put a link in the description. My next guest is Dr. Ben Cook. Ben is a climate scientist at the NASA Goddard Institute, where he mainly focuses on drought and climate extremes, using observations, the paleoclimate record, and climate models. How fast is climate changing now compared to other periods in Earth's history?
Yeah, I mean, I think at least compared to the last, couple of thousand years, the changes we're seeing now are quite rapid and maybe faster than any time we've seen, over the last 2 millennia. I mean, you can go back much further in time. You can find a lot of other periods in the past where we, maybe had very similar, like accelerated climate changes. But certainly what's happening now strongly stands out compared to the last 2,000 years.
Let's talk about how we're able to know what the climate has been in the past.
Yeah, so when we study climate beyond the period that we have thermometers and rain gauges, we have to use these things called paleoclimate proxies. And paleoclimate proxies are just these geologic or biological archives that respond to what the climate is doing in the past. So a really good example that I work very closely with are tree rings. You cut a tree in half, you can see the different rings of growth. Each ring represents a single year of growth. And if the conditions are good, if it's warm, lots of moisture, typically the trees will put on a wide ring. And if they're stressed because it's too hot or maybe it's a drought year, they'll put on a narrow ring. And we can use a variety of statistical tools to basically convert that into information on things like precipitation or soil moisture. There's a variety of other proxies, sediment cores from lakes and the oceans, speleothems, so like stalactites or stalagmites in caves, ice cores, and they all provide different information on different aspects of the climate system.
Okay. Let's talk specifically, about tree rings. There are several things that can be affecting how the tree is growing. Like, how do we distinguish between, how do we know like what is causing what?
Right. So how do we isolate the
Yes,
signal that we want to see in the tree rings?
right.
Yeah, no, it's a really great question. So typically when we want to develop a reconstruction of something like drought from tree rings, we will specifically target locations and oftentimes species that we know are going to be very sensitive to drought. So for example, we'll pick trees that are kind of sitting by themselves on well-drained soils, because we know that those trees, when a drought happens, they're going to be really sensitive and respond really strongly to that. If you were interested in, using tree rings to reconstruct temperature, you might pick trees that are in areas like high elevation areas where they have short growing seasons, so that when it's warm, they'll have a longer growing season that they can take advantage of, and that'll be reflected in the trees. But if it's a cold year, then they'll simply won't grow as well. So there's a lot of kind of art to identifying the trees that are going to best tell you the information you're interested in.
I think another complication is CO2 levels can also affect how much the tree is growing.
Yeah, so there's this thing called CO2 fertilization effect. So basically for photosynthesis, trees need energy from the sun, they need nutrients, they need water, and they need carbon dioxide, because it's the carbon dioxide with the water that they put together to create the sugars and the high energy carbon compounds. If you, all else being equal, if you give plants a lot more CO2, they'll typically grow more because you're just, giving them more of what they need for photosynthesis. In the real world, though, CO2 is, so we do see CO2 fertilization effects, but in general, CO2 is not the limiting resource for most plants. And by and large, we don't see, in some cases we do, but overall, we don't really see a very strong CO2 fertilization signal in tree rings, at least the tree rings that we're using for these climate reconstructions.
Okay, so if you're trying to reconstruct the temperature record, how do we know what's caused by changes in precipitation, what's caused by changes in temperature?
Yeah, I mean, so that can get a little bit complicated, but fundamentally it comes down to the statistical methods that we use to do the reconstruction. So, typically what we'll do is we'll take, the tree ring record. So maybe it, ends in 2000 and it goes all the way back to, like 500 years ago, right? So that's going to have some overlap with the instrumental record, right? So maybe you have 100 years of temperature or soil moisture. And so then what we'll do is we'll take that overlapping period between the instrumental record and the tree rings, and we'll develop statistical relationships using some of that data for model calibration and some of that data for model testing or validation. And oftentimes we'll go through different iterations, trying different statistical models, different kind of calibration validation intervals. And again, we'll kind of like lean a little bit on the domain expertise to, try to interpret the statistical relationships that we're actually seeing.
Mm-hmm.
So in most, if you're looking at trees in the Southwest US, right, where the growing seasons are usually very, very warm, at least not, at lower elevations, the trees are going to be responding mostly to moisture because that's going to be the limiting resource controlling their growth. If you look at trees, at higher elevations in like Canada, right, where, there's usually ample moisture, but temperature is the limiter, in that case, the temperature signal is probably going to be stronger in the trees.
Okay, and then you like leave out some of the data to actually verify that this is giving you the right results.
So basically, we have like maybe we have 100 years of data, and there's different ways to do it, but a very classic way to do it is a split sample calibration validation. So
Okay.
you'll take 50 of the years, you'll develop your model, and then you'll run your model, your statistical model, with the previous 50 years and see if you can do as good a job, right? And this helps prevent overfitting, where you're just kind of replicating noise. And then once you have a model that passes whatever kind of levels of validation that you think are appropriate, then you can kind of use the whole record to kind of look at temperature or precipitation or soil moisture or whatever, much back much further in time.
I want to get into some of the criticisms of that are out there of this. Some of the criticisms are, we don't have a very long period where the proxies and the temperatures overlap. Very minor variations in the model can give you very different results going back a long period of time. And another issue is that starting in the 1960s, there's this divergence where the proxies are going down, but temperatures are going up. And that they've cut out a lot of the data after 1960. Another thing I've heard is that they do some sort of pre-screening where they only use the data that's where there's correlation.
Okay. So let's start with the pre-screening. Okay. I mean, this is like any other scientific enterprise, right? You need to, just like what I said, is, we need to identify the chronologies that are going to give us the best model. And to be clear, we don't stop there, right? Yeah. So we never say like, oh, this thing correlates and then we're going to use that no matter what, right? I mean, we always go through this validation process. Mm-hmm. But, for example, if you sample a bunch of random trees inside a dense forest stand, where the trees are competing with each other for moisture and light, and they're different ages, and there's all sorts of confounding factors, then in those situations, a lot of cases, the noise is going to be so large that you're not going to be able to learn anything, right? So, at the end of the day, we need to identify the trees, the locations that are going to maximize the signal to noise ratio, right? And that's just the first step, all right? And there's nothing wrong with that, right? I mean, if you want to study coral reefs, you're not going to go off the coast of Maine because there's no coral reefs there, right? Like if you want to understand temperature, then you need to find the proxies that are going to give you or that are going to be most sensitive to temperature. Mm-hmm. That's just the first step. But then the next step is the model calibration and validation. Right? I mean, people, will take these data sets, which are all, by the way, completely publicly available, right? So nobody's kind of hiding anything here. And then, you have to, like any other scientific enterprise, right? It's not like there's a kind of always a singular objective way to do it, right? You take the data, and you apply a variety of techniques to analyze it, and you think a lot about the sensitivity of your results to the methodological choices that you make, right? And so that's a lot of what goes into it, right? So that's the kind of next step. And at the end of the day, that's going to give you effectively error bars. So you can kind of you'll have some estimate of temperature, and then once you kind of incorporate these various uncertainties, you'll have the kind of error bars, error structure under reconstruction that can tell you a little something about confidence and how well, for example, maybe recent years stand out compared to the past. Now, is it perfect? No. But, in most of these papers, the validation statistics are there. The process is very transparent. In terms of data is available and techniques are obvious, and people can choose to believe it or not, but the idea that there's some kind of weird nefarious agenda, where every single, tree ring scientist is tweaking their results specifically to get a preconceived, or find support for a preconceived idea is nonsense.
I'm not accusing them of nefarious ideas, but I sometimes think there can be confirmation bias, groupthink types of things that happen in communities.
I mean, sure, but but this is the case for anything, right? Like any kind of scientific community is going to have some kind of, or has the potential for some sort of biases or groupthink. And so look, I can't speak to the motivations. There's uncertainties, right? I think one red herring here is the focus by a lot of people, and not you, to be clear, on the the hockey stick, right? So the hockey stick kind of reconstruction was, one of the first of these types of reconstructions, and certainly one of the ones that became really big. But even within the community, there was some skepticism about it at the time, right? And there have been numerous other efforts that, have generated their own estimates of temperature, that show some major differences, right? So, at the end of the day, all these reconstructions show, this big increase in warming in the recent era, right? I mean, that is, greenhouse gas driven. I mean, that's pretty clear no matter kind of how you kind of do the reconstruction. But oftentimes what you see is that based on different data or different techniques, you'll see differences in the variability in the reconstruction going back in time. So, there's a lot of other reconstructions that have come out then that, showed differences and some agreement. But the idea that everything kind of hinges on the original hockey stick reconstruction.
I mean, but all they all show a hockey stick pattern, right?
Yeah, I mean that's
the critics say they're being done in a similar way.
But I guess I would say you don't even need the trees to see a hockey stick, or that you don't need the chronologies, right? You can just look at the observations. I mean, you look at the observations for the last, probably globally, we have pretty good global temperature observations back to the mid 1800s.
No, I think there is widespread agreement that the climate's warming. The thing I actually am interested in is going back like very far. Like, how unusual is this in terms of the long period of history? Yeah.
Yeah, and I don't think you're never going to find a paleoscientist who downplays past climate events, right, and past climate variability, right? And we know that there are even recent periods where at least regionally there were some pretty kind of interesting things going on, like the Little Ice Age or the medieval climate anomaly, which was kind of focused in the Atlantic sector. In Western North America, we had these multiple centuries of mega droughts, these incredibly intense droughts, that are largely unprecedented, at least in recent times. And obviously you go back even further and you can easily find periods where the climate was much hotter or much warmer than any time in the last 2,000 years. But we have multiple lines of evidence really suggesting that the warming that we're seeing now really does stand out, and it really is being driven by anthropogenic activities through the burning of fossil fuels.
What are the other lines of evidence? Yeah, we talked about tree rings.
Yeah, so you've got the kind of the observational record, right, which kind of tells us with really quite high confidence that it's warming. You've got other reconstructions of other things in the climate system, like sea ice, like sea levels, which again also show these big changes that are consistent with the recent warming that we're seeing. And then we also have climate models, which allow us to look a little bit more at the kind of fundamental processes driving some of these recent changes. So I shared a couple links with you, but basically what we can do is climate models are just fundamentally these computer simulations of the climate system that include all the processes that we think are important. So greenhouse gases, atmospheric circulation, et cetera. Right. And what we can do with these models, and why they offer a lot of power, is we can run them with different forcings, basically different inputs, and we can see how well we actually match the observations. Right. And then we find, and again, I encourage you to kind of look at the links that I sent you, is that we can only get a simulation that looks anything like the observed warming that we see over the last 150 years when we include anthropogenic activities, especially the greenhouse gases. And these models are largely independent from the paleo data, from the observations. And so again, it's just this another kind of line of evidence. What's happening in the climate system now really does stand out.
How good are the climate models of, can they explain like why the Little Ice Age happened? Can they explain the medieval warm period?
No, yeah, that's a really good question. And so it gets a little bit complicated, right? Because you need to not only get the climate models right, but you need to get the inputs right, right? So in other words, like, if you wanted to be able to reproduce like the Little Ice Age, you need to have the right forcings, for what caused the little ice age. You need to be able to put that into your model. Um, the models do, I think, an okay job. I mean, they provide, support for the hypothesis that like a lot of little ice age was probably driven by a kind of bunch of volcanic eruptions and low solar activity that probably cooled things down. The models are not perfect, right? I mean, any model is going to be a simplification of the real system. And so, these models have trouble with things like low frequency variability. So just kind of like slower circulations on decadal, multi-decadal timescales that can, affect things. We test these models in other capacities as well, including against the last glacial maximum, or even like the mid-Holocene warm period.
So we validate the models by looking at temperature records and
okay. So the models are constructed from fundamental like physical equations, right? And then they kind of reproduce a climate as the kind of emergent behavior of these different equations kind of interacting. So for example, there's no there's equations for mass continuity, but there's no an energy, but there's no equation for the jet stream, right? There's no equation for the El Nino Southern Oscillation, right? And so the first test of the models is really like, can the model with the right inputs, like the kind of annual cycle of energy from the sun, reproduce these phenomenon in the climate system that we know exist, like the jet stream, El Nino Southern Oscillation cycles, the Indian monsoon, etc. Right? So that's the kind of maybe like first step. And then, what oftentimes people will do is then they'll take observations and usually compare against the climatologies. So the idea is like, okay, is this model getting this seasonal cycle of temperature and precipitation in these different regions correct? And if they're not, why not? And so, no model is perfect and equally good at all these things, right? And particularly in some regions like East Africa, the models do an incredibly poor job, right? But, when we look at climate models, usually we're not just looking at one climate model, we're looking at kind of multiple models together and looking to see where they kind of agree and where they disagree and how consistent they are or not with the kind of observations we have. The one thing is that we don't fit the models to the trend. Like we don't tell the model, you have to get the warming trend correct, right? We just, again, we have these kind of fundamental equations, and then we can give the model increasing CO2 and see, can the model reproduce the warming trend that we actually observe?
I feel like it is a little more complicated than we just run some physics equations and we get out pops the answer. Like, I feel, aren't there like parameters that we're like unsure about that we have to tune?
Of course, right? We can't explicitly represent all the processes, right? And a lot of that has to do with scale and also just our ability to like observe things like eddies in the ocean, right? Mm-hmm. So yeah, I mean, there's a lot of stuff parameterized. Like a really good example is clouds, right? Because these models tend to be so coarse, right? We can't actually, most of these climate models, do not explicitly simulate like convection processes, like cloud formation, right? So we have to do some parameterizations to basically say like, okay, well, when the relative humidity gets to 100%, like make a cloud, right?
Okay.
So yeah, so there's a lot of parameterizations. That's part of the uncertainties, and that's why multiple models will oftentimes give us, some different answers. So yeah, I mean, it's it's a really good point, right? That's part of the challenge for, using these models. What I will say is I think the models generally do better at larger scale things, right? So for example, if, all the models, to a large extent, with some variation, of course, right, you're going to reproduce the global temperature trend, right? And that's just because, it's greenhouse gases are the main way that we're manipulating the greenhouse gas effect. They're really well mixed. It's a kind of global, kind of integrated temperature. Once you go to kind of more regional scales, though, then you need to be a little bit more careful because then, there's other things that come into play. So, for example, some models have much coarser resolution and much finer resolution. And in topographically complex areas, that can affect, with the climate produced by these models. At the same time, some variables the models are very good at, like temperature, and some they're not so good at, like precipitation. And that's because to get the precipitation right, you need to get so many more things correct in the model. Whereas in the case of temperature, it's a little bit easier, a little bit more kind of straightforward. So, I'm a climate modeler, and, whenever we're using these models as tools to investigate whatever questions we're interested in, we're constantly evaluating and looking at the models and trying to understand, what they're telling us, and more importantly, why they're telling us what they're telling us, and if it's for the right reasons or not.
Okay, I want to go back to something I mentioned about the tree ring stuff. Okay, yeah, one of the critiques that's been made is this divergence problem.
Yeah, so the divergence problem refers to this phenomenon, which is real, where, in recent decades, for a lot of these trees that are used in temperature reconstructions, there seems to be this decoupling between temperatures and tree growth, right? Where it seems like, temperatures will increase and then the trees will simply won't respond. And that's in a lot of areas, it's probably, or it may be occurring due to maybe kind of other limitations for tree growth kind of, coming up. But there's a couple of things here, right? So one is, it is not a universal ubiquitous problem, right? Certainly in some areas, there really is strong divergence, but you can also find sites where there is no divergence, right? And there's also kind of different ways, like we can use the trees that, don't suffer from this divergence problem. So, I mentioned ring widths, but people have also used things like wood density to reconstruct temperature. And wood density, appears to be, at least as far as I understand it, much less sensitive to this divergence problem as well. So yeah, it's there, but again, it's not a universal ubiquitous issue, and it's just, again, kind of part of the process that people doing these reconstructions have to kind of go through.
Other criticism is just like that the uncertainty is higher than they let on. I mean, I don't know who to believe here, but he basically says uncertainty goes to infinity, like back several thousands of years.
I mean, if you're economists don't have the domain knowledge. Tree rings are not just random econometric time series, that, are easy to fit within kind of, whatever kind of preconceived analytical model you might have, right? These are, biological records that are some reflection of all the things affecting how a tree is growing, right? And tree ring science goes back to the 1920s, and so it's about a century old now, and people have been grappling with these issues and these concerns for 100 years. The vast majority of reconstructions that are generated based on tree rings, are credible. And it's, I mean, it's a little hard to talk kind of big picture vaguely, because any kind of singular reconstruction is going to have its own kind of, specific biases and focus. If the issue of concern is the warming we're seeing now, you don't really need trees to know how extreme it is. We have observations, we have fundamental theories that go back a century and a half, and we have the, largely independent climate models that tell us that what's happening now, is being driven by anthropogenic activities. There's no one piece, one domino that you can kind of pull out here and cause the whole thing to collapse, right? I mean, take out any single piece and there's plenty of other evidence.
All right. How worried are you about climate change?
Yeah, I mean, personally, I'm certainly concerned. I mean, do I think it's going to be this world-ending catastrophe? No. But so much of the kind of way that, our societies and ecosystems are calibrated for a much cooler climate, right? And so anytime you're going to start to change things, and shift the underlying baseline into a world where it's going to be warmer, where we're going to get more extreme events, then it's going to have impacts. And so the challenge is figuring out like how best to deal with that. So, I don't think it's not a world ending, but I think it would be folly to pretend like it's something that we can ignore and not try to plan for.
What are the things you're most worried about in terms of future effects?
Yeah, I think extreme events, and sea level rise, right?
Okay.
Because those have kind of direct impacts or relevance for infrastructure, right? So, there's a lot of good examples of this, but, there's a lot of, coastal development in the southeastern United States, right? And even on the east coast of the US. And this is an area where sea levels are rising. And so it means that when we have storms, we're going to get, more storm surges, more coastal flooding, and more impacts on the people and houses that live there. And we can already see in observations increases in things like nuisance flooding. Western United States, much of the development in that region, occurred, during periods of, enhanced water availability, right? But that's an area where the climate models and again the trends, tell us it's going to get drier. And so, but we have all these people there, and so we need to start thinking about, well, how are we going to meet those water needs and those water demands moving into the future?
Let's talk about sea level rise. How fast is the sea rising?
I don't know the numbers off the top of my head, but again, if you go to kind of independent, reconstructions, is that it's rising probably faster now than any time in the last 2,000 years, right? And then when you combine that with the kind of increase in coastal development that we've seen, especially since the 1950s, along with a lot of areas kind of coastal subsidence, we're combined together. It shows in the observations where we're seeing kind of increasing levels of nuisance flooding, of high tide flooding, and increased storm surges that we don't see in records going back to the mid 20th century.
I heard it was rising 3 millimeters per year or something.
Yeah, that might be right. I just don't know off the top of my
Which
head. I mean, the other thing to remember,
seem like a lot.
a lot of these numbers seem small, right? But the thing I always point out to people is, so everybody's like, well, it's only 1.1 degrees warmer, on our planet. Like, how could that be making a difference, right? Well, if you have if your body temperature is 100 degrees Fahrenheit, right? I mean, that's a fever. You feel that. That has an impact on your body, right? These changes don't need to be, that big, to kind of lead to these, kind of bigger impacts, within the climate system. And the fact is, right, like we can see that, like you can look at, these areas, like, and you can see these trends towards increasing flood events, in places like South Florida or the southeastern coast, right? And some of that is land subsidence, but some of that is also like the fact that sea levels are higher, and so your baseline is higher, and so anytime you get these like big high tide events like a king tide, you're just going to flood more of the land that previously would have stayed dry.
The land subsidence, what does that word mean?
Oh, sorry. So in a lot of areas, like particularly like Louisiana, right? These big coastal areas with barrier islands and deltas, they get maintained naturally by basically erosion from the continent. Effectively, these big rivers will carry sediment down and kind of replenish stuff that gets washed away. So in a lot of areas, those rivers, like the Mississippi, have been diked and dammed and diverted, so they're no longer supplying sediment, right? And so, a lot of these areas, it's not all sea level rise. Some of it is like coastal. Well, I don't know, maybe subsidence is the wrong word, but it's, we're kind of cut off the kind of supply of sediment to these coastal areas.
There's also been discussion of like these like tipping points that are.
Yeah. So that, the problem with the tipping point discussion is that there's kind of no real unified like definition of tipping points. Like some people you talk about tipping points and say like, oh, suddenly like a nonlinear kind of shift. Some people talk about it in terms of like hysteresis or irreversibility. I don't know that I personally don't think and kind of focus on those is, the best way to think about climate change. I mean, even if they don't happen at all, there's enough other changes happening that are just kind of steadily continuous, in the background, that, it's the tipping points on some level are maybe a little irrelevant.
How much of the current warming is caused by human activity?
Over 100%. And the
Okay.
reason for that is at the same time that we're emitting greenhouse gases that are warming up the climate, we're also emitting aerosols, mostly through pollution, so little particulates in the atmosphere that reflect some of the energy back out to space and cancel out some of the warming. But you cannot explain any of the warming that we've observed, since the middle of the 20th century without anthropogenic activities.
You're saying greenhouse gases are causing more than 100% and aerosols are causing go down? Is that what you're saying?
Yeah, I mean, so it's a little bit hard to think about, but like when I say about more than 100%, is that if the only thing that humans were doing to the climate system was greenhouse gas emissions, the warming would be higher now than it actually is. Okay. But at the same time that humans are emitting greenhouse gases that are warming the climate, we're also doing some things that are cooling the climate a little bit. A byproduct of a lot of fossil fuel burning are these sulfate aerosol emissions. But the thing is, nobody has offered evidence for any alternative hypothesis to explain the warming. Like the single best hypothesis we have is anthropogenic activities. It does a very good job of explaining the warming that we see. And so any alternative hypothesis would have to do a better job at explaining that warming. And there simply isn't one.
I guess the ones I've heard are solar activity, volcanoes. One person has made a big deal about the changes in ocean circulation, these multi-decadal ocean circulation changes.
Yeah, I mean, we can get into the details of all these things, but again, like we have run the climate models with all of those things, excluding greenhouse gas emissions, right?
Mm-hmm.
And none of those simulations using just volcanoes or just solar activity or just ocean circulation shifts can get anywhere close to the warming that is observed since the middle of the 20th century.
Okay. Yeah. How do we know there isn't more natural variation in the climate?
I mean, so natural variability, right?
Yeah.
That is kind of the kind of internal variability in the climate. So solar variation. Okay. There has been no increase in solar output since the middle of the 20th century. So, and also the fingerprint of what solar inputs would do to the climate system looks different from greenhouse gases. Right. Volcanoes emit CO2, but the rate at which they emit CO2 is multiple orders of magnitude lower than the rate of anthropogenic emissions. Right. So, that cannot explain the increase in CO2 that we're seeing. Right. In the case of like internal variability, yeah. So for example, during an El Nino event, the global temperature is warmer. And during a La Nina event, the reverse, the global temperature is colder. And that's because ENSO does a really good job of moderating the flux of heat between the atmosphere and the oceans. So during an El Nino event, heat comes out of the oceans into the atmosphere, warms things up. During a La Nina event, you have colder tropical Pacific conditions, and that sucks up a lot of heat from the atmosphere and makes it colder. The whole thing about these internal variations, though, is that they're kind of just variability, right? So they go in both directions. And so on long timescales, they kind of cancel each other out, right? Like the only way you can actually get a change in the global temperature is if you actually change the total system or energy balance, right? You need to get a situation where you're trapping more energy than you're sending back, that you have more energy coming in than you're sending back out to space. And there's just no way that ocean changes, could do that over the last like 50 years.
Okay, one of my videos I talk about my videos about the Milankovitch cycles, because I was confused about why, like, we should be in a cold period of the Milankovitch cycles, and I was confused about why we weren't returning to like glacial periods or glacial. And I read this paper that said that like early agriculture may have caused.
Yeah, so there's the Ruddiman hypothesis, right? Which is this
Yes.
idea that, starting with especially like rice cultivation maybe 7,000 years ago, um, and deforestation, and then it kind of increased CO2 levels enough that have like delayed the start of the next glacial cycle.
Yes.
And that hypothesis is still somewhat controversial. I think there's some merit there. But whether it had enough of a kind of magnitude, or if the magnitude of that effect was enough, like to delay the start of the next ice age, is a little bit, uncertain, I would say. Based just on Milankovitch, right? I mean, basically, over the next 10,000 years, we should expect to start shifting into the next glacial period. But again, based on all the evidence from the other glacial inceptions in these ice age cycles, I mean, basically, the CO2 is simply too high now, right? Milankovitch forcing is not strong enough now to cool things enough at these high northern latitudes to actually get the start of these ice sheets and start to kick off the kind of ice albedo and the carbon cycle feedbacks that would allow us to kind of descend into one of these ice age cycles. There have been several papers like recently which kind of highlighted this point that anthropogenic climate change has broken the ice age cycles, at least as mediated by the Milankovitch forcing.
I just feel like there's been lots of claims that this is just very politicized.
The politicization of,
well, yeah, this particular, or
oh, you mean just this topic in general, climate change?
Yeah, the topic in general.
I'm not a political or social scientist, right? In my experience, a lot of the, whether people outside the field kind of believe climate change or not, has more to do with their fundamental identity than, their actual understanding of the science, regardless of whether you're kind of like, accept the science or not. Any science that has some potential policy ramifications, I think is going to, invite, potentially a lot more interest, from the public, because of the kind of at least interpretation that it's going to have a more direct effect on their lives, right?
Mm-hmm.
Like nobody really cares about the Higgs boson, right? Right. And I think a lot of it is because of the kind of perceived kind of policy implications that either align or don't align with their own kind of values and beliefs. Within the scientific community, and there's a diversity of perspectives and a diversity of political beliefs. There is an overwhelming consensus, in support of all the things we talked about today. And it's not artificial, right? I mean, the scientific consensus is really an emergent property, right? I mean, if you really want to be famous, the best thing you can do is to just disprove something that's generally accepted, and then you can kind of stand out as this great kind of thinker. No matter what we try, the single best explanation that explains the trend that we've seen more than anything else is anthropogenic greenhouse gases. And so that kind of sets the bar. And if anybody has, maybe there's an alternative hypothesis that fits just as well, but then the onus is on people offering these other hypotheses to show that they can do a better job of explaining what's happening.
Mm-hmm.
And to date, nobody has.
I guess you got to run here in a sec. Thanks so much for doing this.
Yeah, happy to do it. If you want to chat some more, if you have any questions over email, always feel free to reach out.
Those are the interviews. Thank you to all my guests. My guests had very different opinions about things, but I think we all know who the best guest was. Miljana, obviously.
It is Milutin Milankovic.
Okay, be nice to each other in the comments